before class, we talked about OpenMP, Pitfall. We count just through parameters on everything and except the performance increase. So there are more discussed topics: data dependencies, sharing issues, updating shared values, and parallel overhead. Okay, we can see the one is data dependencies. We can consider the following code. There are dependencies between loop iterations. This code is for loop sentence. So if we see the condition sentence, we can just the iterations is 5,000. The sentence, the important sentence must run 5,000 times. So this is the loop iterations. Okay, splitting this loop between threads does not guarantee in order execution. Out-of-order loop execution will result in undefined behavior. We can see if the for loop run on one thread or run on one core, we can find the 5,000 iterations or 5,000 times must run on one thread or one core or one process. So OpenMP Pitfall, we talk about different dependencies. The two is sharing issues. We can see temp is a temporary variable. So temp is a shared variable. So we can find this is the original sentence. This is the revised sentence. The revised sentence, we can see each thread accesses different elements of A, B, and C. But the temp is same. The temp variable is same. So the temp variable is shared in all scope. So we must see temp must share for A, for B, and for C. The role of this division is to divide three threads. Okay, you can see the three is updating shared variables simultaneously. We can see we can use the array. We can use the array read and write to sum interleaved among threads. This can be done by surrounding the summation by a critical or by a atomic section or reduction clause. So we can see this is parallel for reduction. We must find this sentence is different from this sentence. This sentence is from AI and AI sub 1. This sentence is from sum equals sum add AI. AI is one of elements in array. Compiler can generate higher efficient code for reduction. So we can see the step 4. The fourth topic is parallel overhead. We can see spoiling and releasing threads result in significant overhead. Better to have fewer but larger parallel regions. Parallelize over the larger loop that you can. So we can see after the 4 steps, after the 4 topics, the OpenMP Pitfall can transfer the original sentence to the effective sentence. So this is the last sentence. We can see too much overhead in thread generation to have this statement run this frequently. Poor choice of loop to parallelize. So we can see the red sentence. The red sentence is use temp variable. Temp is share variable. And we can see if we use this function to calculate, we can divide some thread for some thread, for some code, for some process. So you can see OpenMP Pitfall is for parallelize. Okay, this is common OpenMP Pitfalls. The above is the demo of OpenMP. You can see OpenMP Pitfall. Okay, we can see multi-processor cache coherence. Okay, there are two processors. Processor 0, processor 1. We can see recall is multi-threading. Could be spread across multiple cores. So we can see we have two processors, we have two ALUs, we have several registers, we have one main memory, we have several inputs and outputs. This is the structure taught in our class. Okay, multiprocessor cache. Memory is a performance bottleneck. The memory, the speed of memory is also bottleneck in several conditions. We find in several laptops and computers, the memory, the speed of memory is the general bottleneck. If we use the quick memory or the quickest memory, the performance of laptop or the performance of computer can increase and increase. So the memory is general bottleneck in current conditions. So the research of memory is very important for our modern computers. So you can see the memory is a performance bottleneck. Even with just one processor, cache reduce bandwidth demands on memory. Cache have some roles, but cache isn't all roles. Cache can do something to increase the performance of memory hierarchy. So we can see each core has a local private cache. Cache misses, cache hits. We can see cache misses access shared common memory. So you can see this is the interconnection network. This is memory, this is input and output. Some processors have some cache. Some cache is for the processor. We know the level 1, level 2, and level 3. Level 1 cache is simple and different for the processors. Level 2 and level 3 is shared for the processors. So we can see multiprocessor cache. This cache is level 1. This is for one processor. Okay, this is shared memory and the cache. Processor 1 and the processor 2 read memory 1000. This is an array and one dimension array. We can see this is with these 20 variables. These 20 numbers is from the main memory to the cache. So this is the memory source. Okay. Now processor 0 writes memory with 40 numbers. We can see is from main memory. We can see the 40 numbers is transferred to this cache. So we can see if the number of cache is returned to the main memory, the numbers can translate to main memory. So this is from 2, this is twice direction. Okay, we can keep multiple cache coherent. We think the cache and the main memory have the same number. If the number of cache and the memory is different, which is the trusted number? We choose trust cache. We choose the newer number is in cache. So if the number of cache and memory is different, the general solution is replace the cache number to memory number. Okay, keeping multiple cache coherent is very important. Architect's job is keep cache values coherent with shared memory. So the idea is on cache miss or write, notify all other processors by interconnection network. If reading, this is simple. Reading isn't change. Reading can't change numbers. If we use reading operation, the number in cache, the number in memory is the same, and these numbers can't be changed. Many processors can have copies. Copies is same. Copy, yeah. Okay, if writing invalidate all other copies, this is done properly. We can see write transactions from one processor, note tags of other cache using common interconnect, invalidate any keys to save address in other cache. Okay, we can see, for example, now with cache coherence, processor 1 and processor 2 read memory. This memory is one-dimensional array. Processor 0 writes memory with 40. So we can see the processor 0 write invalidate other copies. Okay, the question is which statement is true about multiprocessor cache coherency? We can see there are 4 choices. One is using write-through cache remove the need for cache coherency. 2 is every processor store instruction must check the contents of other cache. 3 is most processor load and store accesses only need to check in the local private cache. 4 is only one processor can cache any memory location at one time. This is the correct, or this is the true. So you can find that every processor store instruction must check the contents of other cache. So you must see this is check and store. Okay, this is the coherency per talk. Per talk is for computer network. Yes, you had studied the course of computer network. Yeah, so we can see per talk is a rule. Yeah, we must obey the rules. We find the per talk is rule. We obey the rule. We obey the protocol. So the protocol is defined by the creators.
Yeah.
So we must obey. MOESI is a symbol of coherency protocol. Okay, we can see how does HW keep coherent. The simple protocol is MSI. MSI are three words. One is modified, one is shared, one is managed. So MSI is one of the first calculator of three words. Modified is up to date, changed, or okay to write. Changed is equal to dirty. So the dirty data isn't means the data is dirty. The dirty data is duplicated data or changed data. So the dirty data in database or in data sets is very general and is very common. So we find if you become a database engineer in the future work, you can find dirty is good and dirty is common.
Yeah.
So your files in your laptop or computer have some dirty data. Shared is up-to-date data, not allowed to write. Shared, we can share some data. We can see other cache may have a copy. Copy in memory is up-to-date, but shared isn't allowed to write. Shared data is obeyed to read, don't write. So shared is limited by some operations. Invalid is data in this block is garbage. So invalid is garbage. Invalid is unuseful. So the invalid data is garbage. So MSI is MSI. This is simple protocol. And each cache tracks state of each block in these three operations. Okay, this is MSI protocol. MSI protocol has three states: invalid, shared, and modified. The three states, the transportation of three states, you can see some direction and some condition. If we have become invalid to shared, we must see this is the condition. Read miss. This means get blocked from memory. If we want becomes shared to modified, we must obey the condition write hit. If we want modified, repeat and repeat, you find this is the condition read hit and or read hit or write hit. This is the condition. Okay, this is MSI protocol. This is current processor. This is response to other processors. We can find this states is different from this state. We can see a prior heap means a prior file is requested block in another cache. Prior is another processor. So prior is a symbol. The symbol is another processor. Okay, the question is how to keep track of state blocks in if we can find already have value date bit at 30 bit. We can introduce a new bit called shared bit. So MSI, the value bit is 110. The 30 bit is 1010. random. The shared bit is 0, random, random. The X means doesn't matter. Doesn't matter is random. Okay, this is MSI example. There are two processors in MSI examples. We can find here there's only one other processor, but we would have to check and evaluate the data in every other processor. We can find in the main memory we have two blocks, block 0 and block 1. So we can see processor 0 and the block 0 read, processor 1 and the block 0 read, processor 0 and block 0 write. Yes. There are some operations. Okay, this is compatibility matrix. Each block in each cache is in one of the following states: MSR, M modified, shared, invalid. But invalid isn't in cache. Modified and shared is in cache. This is correct because invalid data isn't useful. So we don't want invalid data in the cache. We hope the data in the cache is useful and frequently used. Okay, this compatibility matrix can allow states for a given cache block in any pair of caches. Okay, this is the problem of writing to share is expensive. If block is in share, we need to check if other caches have data. If block is in modified, we find we don't need to check other caches if we want to write. This is the answer. Only one cache can have data is modified. This is very important. Only one cache can have data is modified. If several caches have data is modified, we don't know which one is the modified. So we check, we give a rule, only one cache can have data is modified. Okay, this is performance enhancement solution. The solution 1 is exclusive state. We can give new state. In the former, we can see we have three states, MSI. Yeah, but you can see the name is MOESI. So we can see MO is added in the revised talk. Okay, we can see exclusive. Exclusive is up-to-date data. Okay to write. No other cache has a copy. Copy is in memory, up-to-date. The write memory is float replaced. Supplies data on read instead of going to memory. Now, if block is in share, at least one other cache must contain it. The share, we can see this is one new state. The share is up-to-date data, not allowed to write. Other caches definitely have a copy. Copy in memory is up-to-date. So MESI, also known as denoise protocol. So this is MESI. Okay, the later is MOESI. MESI is the revised protocol from ESI. So MESI is revised protocol. Okay, we can see invalid, shared, modified, and exclusive. Yeah, this is MESI. Yeah, we can see we added exclusive state. We can see if we want to become exclusive state to modify state, we have obeyed the right heat on this condition. This is heat isn't missed. Okay, MESI per port is response to other processors. So if the prime is another processor, repeat this condition obeyed, the exclusive can become shared. You can see this is become modified, this is become shared. This state transportation, the state change isn't safe. Okay, how to keep track of state block is in. We can see we add exclusive number or exclusive rules in the table. Okay, the problem is expensive to share modifier. In MSI and MESI per block, if we want to share block in modified data written back to memory. Modified block can become shared. Block that once data can become shared. So writing to memory is expensive. This is the question. Okay, the performance enhancement 2, solution 2 is owned state. Own is, this is mine. Yeah? Owner is up-to-date data. Read-only is like shared. You can write if you invalidate shared copies first and your state change to modify. So owner is the owner. We have something. We are owners. So we want owner, treasures, money, and some good things. So owner is the owner. Owned state is the state of owner. Other caches have a shared copy. Now we can see this is shared state. Shared state is the wanted state. In China, in the former, we talk about shared house, shared bicycle, and shared and everything.
Shared house?
Yeah. Shared house isn't existing. In China, we have a hope, 共产主义. Yeah. This means everything is for everyone. This isn't in fact in current years this isn't existing. So in China we are similar for Western countries and Western modern countries. So own is correct. Owner supplies data on prime read instead of going to memory. So combination of modified and shared. Shared is up-to-date data, not allowed to write. So shared is good state. We want the data is shared for every user. So if we have some research results, we want to publish some papers and publish some materials in the website. So you can find some shared website to share the materials to everyone. So if you do some research work in the future study or in the future working period, you can search some shared data sets and materials from website. So I and my students share and but share the data from both sides. So we like Google. The Google is for share. The share is the main idea from Google company. Yeah. Okay. Our cache definitely have a copy. A copy in memory may be up to date. Common cache coherency protocol. This is N protocol. This is MOESI. So you can see this. There are 4 states. MOESI, modified, owned, exclusive, shared, and invalid. So this is the truth table, and we can find each block in each cache is in one of the following states. This is mean correct. Yeah, this is mean random. So capacity matrix allows states for a given cache block in any pair of caches. So this is MOESI. Okay, Snoopy protocol is another term of MOESI. Some people feel the MOESI is difficult to read. So Snoopy is another name. So cache coherency is very important. We must keep cache coherency. Okay, this is 5. There are 5 states in the image. We can see modified, exclusive, invalid, shared, and owned. So the owned is related to modified. So you can see in the image, modified is important. You can see every state is related to modified. You can see 1, 2, 3, 4. These 4 relations can describe the modified must related for other 4 states. Yeah. So modified is very important. In the cache, modified is frequently operations. Okay, this is response to other processors. We can see prime. If we have prime right it, we can become exclusive to invalid. Okay, this is the table we have added on the state. Okay, this is MOESI example. So block 0 is never unnecessarily indicted, and we don't waste bandwidth writing to memory. This is the current state. Okay, this isn't clear. Cache coherency checked by block. We can see this is an interconnect. The above have two processors and 2 caches. We can suppose block size is 32 bytes. P0 is processor 0. Reading and writing variable X. P1 reading and writing variable Y. X in location 4000. Y in 405 or 4012. This is the address. This is 4000. This is 4012. So you can find the 4000 is for processor 0. This address is for processor 1. So we need a way. The 2 processors have 2 different addresses. If the 2 processors have same have same addresses, this is collusion. Yeah. So we need a way. Different processors have different addresses. Fault sharing You can see block ping pong between two cats. Ping pong is ping pong. Yeah, ping pong is a sport in China. Between two cats, even through processors are accessing disjoint variables. We can see effect called false sharing. How can you prevent it? The two is, one is want to place state on different blocks. Two is reduce block size. Okay, this is false sharing vs real sharing. We can see if we have the same addresses, if the same piece of data being used by two cats, ping pong is inventable isn't good. This is bad condition. This is not false sharing. Good catch invalidation occur if block size was only one word. If yes, this is true sharing. If no, this is false sharing. Okay, we can see understanding catch misses on 3 C's. The 3 C's is compulsory, capacity, and conflict. Conflict is condition. Condition is the thing, and this is problem. Compulsory, first access to a block in memory impossible to avoid. A solution is we can use block size. We can increase block size. Capacity solution is cache size. We can increase the cache size, and we can use increase cache size. The solution of cache size. The solution of increasement cache size to may cause the access heap time. Conflict solution. The solution of conflict is we can increase cache size. We can increase a social activity. This is 2 effective solutions. Okay, false C. There are 3 C's. This is false C. False C is coherency misses. Misses caused by coherence traffic with other processors, also known as communication misses, because represents data moving between processors working together on a parallel program. For some parallel programs, coherency misses can dominate total misses. Okay, this is the summary of lecture 23. The summary has 2 sections. One is OpenMP. OpenMP and simple parallel extension to C. We can see synchronization accomplished with critical or atomic or reduction. Pitfall can reduce, speed up, or break program logic. Cache coherency implements shared memory, even with multiple copies in multiple caches. So we can see false sharing. Okay, this is the content in lecture 23. Okay, we can see 24. Okay, 24, the topic of 24. In 24 is warehouse scale computers and MapReduce. MapReduce is for big data. Big data is modern technology in current organization. So the MapReduce, high-dose, and other structures is for big data technologies. So we find big data, and big data is modern technologies. So people like to discuss. So we can see warehouse. Okay, this is review of lecture 23, OpenMP, catch coherency. We can see catch coherency implements shared memory, even with multiple copies in multiple caches. We want the data in cache is simple and is single. The protocol we learned was MOPSI or floating. False sharing renders a block of useless, a ping-pong chain of invalidation. Coherency misses are the false cache mistype. So this is agenda in lecture 24. The fourth section is warehouse scale computers, cloud computing, request level parallelism, and the MapReduce. Okay, if we have some times in the following classes, we can talk about some ideas or some knowledge about all big data. Yeah, big data is useful. Okay. So great idea 4 is parallelism. So we can see the topic in lecture 24 is parallel request. We can see assigned to computers. The hardware have warehouse, scale, and computer. Warehouse is developed by database. Yeah, database is useful software, useful system software in operating systems. So in banking, in communication, and in other companies, we find the warehouse and the database is useful and frequently used. So if we call and recall and send message and do something, we must pay some cost for the communication companies. If we don't give the cost to these companies, we can't use these services. So hardware is very important. Okay, we can see this is computer areas of mainframe 1950 to 1960. Okay, you can see Big Iron. Big Iron is from IBM. Univac build 1 million computers for businesses. Global Fortune and time sharing operating system. Time sharing is an important solution for operating system. Yeah, time sharing. Yeah. If I have 1 hour for three students, we can cut 1 hour to 20 minutes.
Yeah.
I can choose the 20 minutes
for each
classmates. Yeah. Each classmate means feel I have separated time to talk with teachers. So time sharing is the solution for operating systems. Okay, Fortune is another programming language in the past. IBM Univac is the computer in the past. Big Iron is one symbol. You can see this is some computers, and this has some computers. The computer, yes. Okay, you can see this is processor is CPU.
Yeah.
In the past, we don't have GPU. GPU is developed in nearly 10 years. So the CPU is an important section in the past computers. Okay, IBM is one famous company in the past, but in the future, in the current, we find IBM company is become low and low. The role of company, the role of IBM company. The IBM company had produced some famous computers, but in the current era, we find IBM, the famous product from IBM is less and less. Okay, this is some mini computer era from 1970s. From 1970s, we can see the computer is different from current. Yeah, we can see using integrated circuits. Digital HP is weak, but HP is another company in America. Yeah, HP in China we call Hui. Yeah, this is another company like IBM. IBM is the symbol. Computers for labs, universities, we can see C programming language and Unix operating system. Unix operating system is the base in Mac. Yeah, we can see the Unix, the Macintosh or Mac operating system is based on Unix operating system. Please pay attention, Unix, not Linux. Linux is free. Unix is paid. Okay, this is PC era from mid-1980s to mid-2000. The computer is when I was in the state student era. I see the first computer is like this. Yeah. In the past, this is the monitor. This is the computer. This is the keyboard, and this is the soft floppy. Yeah. Okay. You can see the size of monitor. I remember in the past the size is 40 inches. 14 inches or 15 inches. You can see in the current the size of monitors we have 23, 27, or 34, or 42. Yeah. So the size of monitors become big and big. Yeah, we like the big monitors. In some working condition, I see some engineers have 3 monitors. Even some engineers have 6 monitors. Yeah, he sits in the center. So 6 monitors divided from left, middle, and the right. This is useful conditions. Okay. Yeah.
Why they are using like that, like 2-3 monitors?
Please repeat.
Why they are using like that together 2-3 monitors? Just use that some developers use the 2-3 monitors.
You ask use the monitor?
He said why they use so many monitors? Why they use so many monitors?
What is why the monitor?
Why they use so many monitors?
Some financial engineer. Yeah. Some financial engineer must use several monitors. If I have software monitors. If I am a software engineer, the common condition is 2 monitors. Yeah, the left and the right. Yeah.
Question mark.
Okay. We use 2 monitors for useful conditions because the left monitor we can put this rectangle. The right we can use this condition. We write some paper, write some documents, write some materials, and read some materials is in one. We write and read some codes in 2.
Okay.
So you you sit in this center. So the distance is very near. So 1 and 2, we do some different works in 2 monitors.
Okay.
Okay, you can find some computers can output several video signals. You know, VGA, the video card can output several signals to several monitors. The computer in our home, in my home, the video signals are 2. But I used 1 monitor because my monitor is 34 inches. So the size is too big. It's occupied by my desk. I haven't the space. But if I have conditions, we won't use 2 monitors. If you use a big monitor, you can put some window from left to right, and this is useful.
Yeah,
Yes.
understood.
Yeah. So if I had used the monitor in the past, we don't like. Using microprocessors, you can find Apple, IBM, use 1 key computer for 1 person. You can find the cost is become low and low. Basic Java Windows, Basic Java is another programming language.
Yeah.
The Java is from Sun. Sun is another famous company in America.
Yeah.
Windows OS is from Bill Gates. Yeah. We also know Windows operating system is for several people and for all people. So in China, Windows OS is free. In China, no other users want to pay some cost for Microsoft company. So Microsoft company it has no solution for this computer. PostPC era. What is PostPC? We can see PostPC is mobile PC. Yeah, mobile. Yeah, we can see this is cell phone. We can find the cell phone. The use of cell phone is become power and power. So we can find this cell phone. This smart cell phone is like microcomputer.
Yeah.
Yeah, so we can use some app to choose, to discuss, to give some solution. So app is useful, but in current architecture, the architecture of mobile cell phone, we find we must use several apps to solve several problems. If we had developed or we had created one software to including several apps. This is useful. WeChat wants to archive these components. So in WeChat, small programmer 小程序 in WeChat 小程序 is the useful solution, but the 小程序 微信小程序 the use of 小程序 small program is limited, so we must use apps. Because, for example, if I want to buy a coffee, we must open the app for LinkedIn or Starbucks. Okay, this is personal mobile devices is PMD. So the cell phone, the PostPC Era is from 2000 to the future. So you can see Object-C, Swift, Java, Android OS, and iOS is the technologies. iOS is from the past to the current and to the future. So we like the iOS. We feel the iOS, the use of iOS is simple. We like to use iOS and the Windows. So iOS in China has many users. If you have chance, you can go to the iOS market and to try the iOS. Cloud computing using local area networks. Amazon Google is famous company in America. Amazon is for buying and buying. So Alibaba and Pitfall is Chinese Amazon. Amazon is created, or Amazon is founded in several years. So in China, because China has many people, so Amazon in China is very limited, because if we buy something by Amazon website, this is too slow. I had buy something by Amazon. I found the period of waiting is too long. So we like to use Taobao. We like to use Jingdong. This is 2 days or 1 day. If the product is in the local warehouse, 1 day. If I put an detail, if an order and details in afternoon, in the morning, in afternoon, the product can transmit it to my home.
Jingdong is JD, right?
Jingdong has several warehouses in several cities. Jingdong is from package. He's strong. The strong use or the strong characteristics of Jingdong is package. His first service is for package. Okay, cloud computing. Google. You can see if we have time, we can talk about some big data and cloud computing. You can find Google is famous company. A lot of famous technologies are from Google. And these famous technologies are free. Android operating system is from Google. Yeah, but Google hasn't paid. Don't want any company to pay.
But Android also created from Linux.
Yeah.
So we also use free.
Yeah, this is correct. Samsung in Korea, I remember, Samsung company in Korea is recovered by Android operating system. In the past, the cell phone of Samsung is unusable and sell several amounts in China. But if the Samsung cell phones add Android operating system, the Chinese people like the cell phone. And the Apple cell phone is created by in 2004. I can't remember, but in this period, the iPhone is created, so the Chinese people like buy. Yeah. Warehouse scale computers, we can see internet service for PMD, MapReduce, Ruby. This is some technology for big data, especially MapReduce. MapReduce is a good technology from Google. This technology is created by 2005 or 2006. Yeah, so this is created by, this is the basic technology of big data. Okay, we can see why cloud computing now. This is the workspace race built out of extremely large data centers, built out driven by growth in demand. Infrastructure, software, and the operational expansions discover the economy of scale and more pervasive broadband internet so can access remote computer efficiently. This is some conditions. Okay, in November 2019, we can see this is the price. We can see this is the price. The price is become low and low and low. We want the per hour, the price of per hour, cost of per hour is become nearly zero. If the price is become low and low, the cost of users is become low. So we want the change. So cloud computer in WSC example is standard to multiple extra large. At these low rates, Amazon can make money. EBS is elastic block store. This is EBS. SSD is solid state disk. We talked about in the former class. HDD is hard disk. Yeah, so you can find this is low than this. Yeah, this is very cheap. This is cheap. So we want this price, nearly this. If the price become low and low, so we want to buy a big and big SSD. For example, I had one laptop occupied 128 GB. If the SSD become low and low, we can use 1 TB SSD. The SSD is very quick. Each also comes with dedicated attached SSD if you choose and pay for that. So this is from Amazon website prices. You can find this is instance and prices. Okay, today is enough. We can talk about in next week, in next Tuesday.